Optical imaging plays a crucial role in both theoretical research and daily life. Conventional optical imaging methods measure the intensity distribution of the optical field, acquiring object information through first-order correlation characteristics, intensity and phase, of the optical field, as exemplified by microscopes, cameras, telescopes, etc. Scattering imaging, also known as single-pixel imaging or ghost imaging, is a novel imaging technique that has gradually developed over the past decade. Compared with traditional imaging methods, scattering imaging relies on the correlation measurement between the speckle field and the object's optical field intensity, belonging to the second-order correlation of the optical field. Scattering imaging reconstructs the object's image by establishing a second-order correlation algorithm model and performing correlation calculations between the signal light intensity passing to the target object, the object light intensity measured by a bucket detector, and the reference light field not passing through the object, the pseudo-thermal light field detected by a CCD, or the calculated speckle distribution light field. This technology achieves the separation of detection and imaging, representing a non-local imaging method, i.e., standoff imaging, and is therefore also referred to as ghost imaging. Conventional pseudo-thermal light correlation imaging. In conventional ghost imaging setups, a laser beam passing through a rotating ground glass diffuser generates a pseudo-thermal light field, where two correlated beams propagate through separate optical paths. The signal beam illuminates the target object and is collected by a spatially non-resolving bucket detector, while the reference beam propagates freely without object interaction, and its intensity distribution is recorded by a CCD camera. Image reconstruction is achieved through correlation computation between the spatially resolved intensity distribution measured by the CCD and the total intensity detected by the bucket detector. Computational ghost imaging. The principle of spatial light modulator, SLM. Base ghost imaging replaces the rotating ground glass diffuser in conventional ghost imaging systems with an SLM to achieve programmable control of the illumination field. Based on scalar diffraction theory, the intensity distribution of SLM-modulated light received by the CCD detector can be computationally predetermined, thereby eliminating the reference beam path while simultaneously reducing computational complexity. The system is principally composed of two key components: the hardware optical system and the software algorithms. The hardware optical path primarily consists of laser source, beam expansion system, SLM, lens, beam splitter prism, target object, lens, bucket detector, oscilloscope, attenuator, lens, and CCD camera. The software algorithm module comprises dedicated ghost imaging software designed to fulfill specific functional requirements. The system supports synchronized operation with CCD cameras and oscilloscopes, enabling acquisition signal storage and export functionality. It features random speckle pattern generation capability and supports importing algorithm-designed images for loading onto the SLM. Both the number of speckle patterns and image resolution are adjustable. It incorporates correlation computation functionality, enabling joint processing of images captured by the CCD camera and signals acquired by the oscilloscope to reconstruct the object's image. It is currently equipped with a transmissive amplitude mode SLM model, TSLM07U-A, featuring 1920 by 1080 resolution and 380 nanometers to 1200 nanometers spectral range. This spatial light modulator demonstrates exceptional performance in generating controllable, pre-calibrated speckle patterns.